Alrighty, let's talk some structure here. 1.6 gets us into how methane actually looks, what its actual structure is. So let's remind ourselves about what carbon is. Carbon has how many? 4 valence electrons it forms. In order to get up to the 8, it has to form those 4 covalent bonds. So in carbon's valence shell, the atomic orbitals look like this. 2s will have 2 electrons, right? Because 1s had 2. So carbon has those 4 valence electrons. So 2s2 gets filled up. 2p, one of them in the first 2p, and then one of them in the second 2p, right? So if all we had were these orbitals this way, valence bond theory might suggest that each of those orbitals would overlap with the hydrogen to make a bond. Okay? So could it be even, possibly you could imagine promoting one of those 2s electrons up into a 2p. That way we'd have 4 unpaired electrons. That would be at least consistent with carbon making 4 bonds, right? But if that were the case, that would suggest that a 2s is overlapping, that little spherical one in the middle, and then each of the 2p's were overlapping. So that would give 3 bonds of one kind and 1 bond of another kind, right? You'd have 3 similar bonds to each other. Let me go to my model here, right? Remember, here's S, the spherical one, right in the middle, 2px, 2py, and 2pz. So one way, and scientists actually thought this might have been the case before they figured out the tetrahedral shape, but if we had an unpaired electron in each of these, then maybe somehow the spherical one could overlap somewhere, and then we'd have bonds going out in 3 sort of right angle directions from each other. Right? That's sort of what it would have to be if those were the orbitals that were overlapping with, say, hydrogen in order to make methane. Now, it turns out that, like we said before, the actual structure of methane, CH4, is tetrahedral, and it has 4 identical bonds. So here's that tetrahedral shape that we mentioned before, right? 1 up, 1 down to the left, 1 forward, and 1 back. Well, how is it that the orbitals that we discussed up above, how is it that those can be overlapping somehow with hydrogens in order to make this kind of geometry? There's nowhere in these actual orbitals themselves where I've got 1 up and then 3 that are sort of going down like a tripod. And even so, we have this s orbital that's in the middle of the atom that's going to really have a hard time overlapping with another atom at all. It's just all sort of in the middle of that carbon atom, and there's nothing really sticking out that can overlap with a hydrogen. So this tetrahedral structure, something has to happen in order to make that. So in order to make 4 equal bonds, the single s orbital and the 3p orbitals must combine together. So I have those 4 orbitals in the valence shell. They're going to sort of blend together, and they're going to make 4 new orbitals that are all the same. Okay? That process is called hybridizing. So what we formed here, they're called sp3 hybrid orbitals. So let's just draw a little bit here, and I'll show you what it is. If we do the ground state, if I have electrons in their lowest possible energies, right, that's what we would have unhybridized. Okay. Now, maybe we could possibly envision promoting one of those electrons up and changing its spin. Okay. That would at least distribute those electrons if we're preparing to make 4 bonds. But this hybridization process will combine these 4 orbitals, right? 3 of the p orbitals and then 1 of the s orbital into 4 equivalent sp3 hybrid orbitals. So each of those will now have 1 electron, and we'll have 4 of equal energy. So it's called sp3 because there's 1s that I combined, and there are 3 of those p orbitals. Okay? That number 3 there is a number just like in electron configurations, like 1s2, 2s2, and so on. Okay, so that's how we can envision their energies anyway, right? We took these unequal, we blended them together. In a activity in class, we'll take different colors of Play-Doh and actually mix them together and get a hybrid color that's in between. Okay? Let me go to my 3D drawing here. We started with 1, 2, 3, 4 orbitals, 1s, and then 3 of those p's. When they're hybridized together, I get 4 identical sp3 hybrid orbitals. Now, look at how these are arranged. This is that tetrahedral shape we talked about, where I could have 1 going up and 3 going down if I wanted to. I could have 2 down and 2 up if I wanted to, but they're all 4 things poking out in, they're spread out around that central point. This tetrahedral shape is the way that 4 things will actually spread out. Now, these hybrid orbitals kind of look like balloons in this picture here, and you could even try this yourself. If you took 4 balloons and you tied them together at the knot, they would actually form this tetrahedral shape, because this is how 4 things will arrange themselves in space, right? So there's the sp3 hybrid orbitals. Now, what we end up with is 1 electron in each of these sp3 hybrid orbitals that's allowed to overlap with a hydrogen. Okay, so here are the 4 valence electrons for carbon. Here are hydrogen's electrons, 1 in each of those hydrogens. Okay? That's where carbon gets its 4 bonds. When we combine those together, the carbon will have access to 8 valence electrons. Right? So maybe I should draw it like that. Alrighty.